Hello friends, welcome to the second part of this video about the implementation of the restoring division circuit. The objective of this second part is to further explain how to implement the circuit for the restoring division of binary numbers. In the previous part 1, we explained the design of the block diagram circuit, how the computer handles the registers, and an example of implementation. If you haven't seen it, I recommend you to check it first. This is the block diagram of the restoring division circuit, already introduced in the previous video. In red, you can see the three registers. This is the register of the divisor. This is the register of the quotient that is given a double use. Initially stores the dividend and then progressively is substituted by the bits of the quotient. In this register is where at the end of the process the quotient result is shown. And this is the accumulator where the partial reminders are stored. Initially is set to 0 and then at the end of the process becomes the final reminder. This is the control logic unit from where the add, subtract and shift operations are controlled. And this is the other processing unit. During the process, the value of these registers change according to the steps of the operation. And at the end of the process, the final values of the registers Q and A show the final quotient and the final reminder. In order to simplify the design of the control logic unit, let's focus first on how to take advantage of the other block and the carry bits. For this, let's see first the design of the other block. This is the typical circuit of a ripple carry adder with small modifications. Each stage is made by a full adder. In earlier videos about adders, we have already seen how an adder circuit can be converted into a subtractor by simply using a 2's complement input. This is what we are doing here. As you can see, the only small changes we have done are to introduce an inverter in the B line to get the 1's complement of B. B is the line coming from the divisor register, and A is the line coming from the accumulator register. The second thing we do is to introduce a C0 equal to 1 as an input carry in order to add 1 and so to convert it into the 2's complement. Remember that to perform a subtraction of two numbers A minus B is equivalent to perform the addition of A plus 2's complement of B. For example, to perform a subtraction of 13 minus 6 is equivalent to perform the addition of 13 plus 2's complement of 6. Important. Note that in the result we get a carry bit. So, in a subtraction, when the result is positive, we get a carry bit of 1. Similarly, in a binary division, the subtraction for the partial remainder can be positive or negative. When the result is positive, the carry bit is equal to 1. Also, as you know, when the partial remainder is positive, that means that the division, it goes. And when the division, it goes, the quotient bit is 1. So, the conclusion is that we can directly use this carry bit as our quotient bit. We can directly use this carry bit as our quotient bit. So, the bottom line is that in our circuit, the control unit can use directly this carry bit as the quotient bit in the step of our flowchart, because if A minus B is positive, the carry bit is 1, so we can use it directly as Q0 equal to 1. And if A minus B is negative, the carry bit is 0, so we can use it directly as Q0 equal to 0 in the restoring step. So, the same carry bit issued from the other can be used for the quotient Q0 bit. So, up to now, we have found already from where to take the quotient bit Q0. Now, looking at the flow diagram steps, you may have noticed that the only thing we need to complete the circuit is to add a device that can restore the original number if the value of the subtraction is negative. For that, we can use a multiplexer. This is the circuit. A and B are the inputs. This is the inverter. This is the full adder, same as in the previous slide. This is the input C0 equal to 1. This is the carry output, which is 1 or 0 depending if the subtraction is positive or negative. This is the multiplexer, and this is the multiplexer selection input. When the carry is 1, the output is A minus B. When the carry is 0, the output restores A. So, this is the circuit that is used to restore the original number if the value of the subtraction is negative. If we combine n such blocks, we obtain the subtraction and restore circuit for n bits, from which we can perform the n-bit subtraction along with the restore operation. So, as you can see over here, the carry output of the last block is taken as the selection input of each multiplexer, the selection input of each multiplexer. So, if the carry is equal to 1, the output of this block is equal to A minus B. But if the carry is equal to 0, then the output of this block will be equal to A, that means restore. So, in this way, we can perform the subtraction and the restore operation together. If we combine n such blocks, then we can perform the n-bit subtraction along with the restore operation. Each block highlighted in blue is called the Restoring Division Processing Unit, PU. Now, along with the subtract and the restore operation, we also need to perform the shift operation. This shift operation is performed here by properly arranging the blocks of the processing units PU. This is the example of a circuit that performs the restoring binary division of 4 bits by 2 bits. 1, 2, 3, 4 bits for the dividend, 1, 2, 2 bits for the divisor. Each stage or each row represents one iteration of the division. In red is the multiplexer line. As I explained before, depending on the final carry of each row, each processing block performs either subtraction or restore operation. And the quotient bit is 1 or 0, same as the carry. Since in this example our dividend is of 4 bits, we have a total of 4 rows. 1, 2, 3, 4 rows. That means at the most we will have 4 iterations equal to the number of bits of the dividend. Now another question is, in each row, how many processing units we need to add? In this example, since the divisor is of 2 bits, in the first 2 stages we will have only 2 units. 1 unit, 2 units. 1 unit, 2 units. And after that, in each stage, we will have 1 more unit. That means in the last 2 stages, we will have 3 units. 1, 2, 3, 1, 2, 3. And as you can see, in each additional unit of the last 2 rows, the input is 0. 0 and 0. If we take another example, in the case of a 5-bit by 3-bit division, the number of processing units we need is the following. Since the dividend is of 5 bits, we have a total of 5 rows. Since the divisor is of 3 bits, the first 3 stages have only 3 units. And after that, in the next 2 rows, we need 1 more unit. That means in the 4th and the 5th row, we will have 4 processing units. And in the additional units of the last 2 rows, the input is equal to 0. So the question is, why we need more processing units when the rows increase? The reason for needing 1 more processing unit in the 4th and the 5th row is because as we bring down more dividend bits, the partial remainder grows in width. Initially, we only need 3 bits to compare with the divisor. But after the 3rd stage, we have already shifted in enough bits from the dividend, then the partial remainder can be 4 bits wide. So, as the partial remainder grows beyond the divisor bit width, we need extra subtractor processing units to handle the wider remainder. So we add extra processing units with 0 inputs for the divisor extension. The reason for feeding with 0 inputs is because the extra processing unit doesn't correspond to a real divisor bit. Instead, it gets a 0 input, effectively aligning the 3-bit divisor with the 4-bit remainder. Note that as the number of bits in the division increases, then the required number of processing units are also increasing exponentially. That is why when programming, the division circuits should be avoided whenever possible in favor of other much simpler solutions. In summary, in the present video, from the block diagram of the restoring binary division circuit, we explain in detail each block circuit, such as other subtracting and restoring circuit using the 2's complement, how to use multiplexers combined with full adders for the design of the circuit, the handling of the computer registers, the final logic layout of the binary division restore circuit, and why we need more processing units when rows increase. And concluded that, when programming, the division circuit should be avoided whenever possible in favor of much simpler solutions. This is all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. And some final considerations. The present video, together with the part 1 and the practical examples included, completes the hardware implementation of the restoring division circuit. The restoring algorithm is applicable to both signed and unsigned numbers, but for the application to signed numbers, it requires from ESTA logic to handle signs. This resulted in the development of a new method called the non-restoring division. This new method and associated algorithm is more efficient and becomes more commonly used for signed division compared to restoring division. Thank you. In the next video, we will explain how to implement the non-restoring division algorithm.